Hello, this video is for folks who missed some of the instruction about how to find the energy per charge, the voltage the charges carry through resistors in circuits that aren't series or parallel, and also to find the current, the speed of charge through those resistors. This is a little bit like a puzzle. I hope it's something you'll enjoy. But the process is first, you try to figure out the total resistance of the circuit. The reason for that is once you have the total resistance, you can start getting the total current. Once you have the total current, you can start working your way back and finding the current through various pieces. So we're going to basically ignore our goal of filling out this table and finding the voltage and current of each resistor. We're going to start by simplifying the circuit. And we're going to take the simplest piece we can each time, combine the resistors in it together, and repeat ourselves. The only thing we know to begin with are the resistances, and we know the total potential difference, the total voltage, is 48 volts. So let's get started. When I first look at this circuit, I see that a charge starting at the battery, a coulomb of charge could be given 48 joules. It could spend some of that energy here, other energy there, and then be back where it started. We could call that I1. A different charge starting in the same place could spend some of its energy here, some here, and then back home. That's a different pathway than the first charge. We'll call that current 2. So some resistors like the 20 are going to get charges that are in both loops moving through them. Some are going to get just current 2. Some are going to get just current 1. So when we're trying to decide what the simplest place to start is, we need to look at who's only getting one current. And I think that tells me that the simplest resistors to probably combine are the 15 and the 35, because they are in series with each other. So let's draw a new version of the circuit. It's electrically the same thing. We're just going to combine these two into one resistor that has the effect of both. So I got the same battery. I haven't touched this resistor. I haven't touched that one. But now these guys will be combined together. In a series circuit, resistance is just add. So this is a 50 ohm resistor. Let's take a look at what our current tells us now. The charge could still go the way through the 40. So we still have I1. Or it could still go this way. So we still have I2. So now looking at this, the 20 ohm resistor seems the most complicated because it's getting charges going through it that take two paths. But this guy is directly connected to this guy. They each have one current through them. I think these two guys are in parallel. So our next step is going to be to make them into a resistor. So I'm still going to have my 48 volts. I'm not messing with that 20 ohm resistor. That's the last one I'm going to touch. But now I have a new RP, which I'm going to get by combining these two together. So this is when we use the resistors in parallel equation. And honestly, at this point, we should probably just decimalize this. So I'm going to do parentheses 1 divided by 40, parentheses plus parentheses 1 divided by 50, parentheses equals. So 1 over RP is 0.045. And now we'll just invert it. 22.22222222. So now our scary circuit's looking a lot less scary. And I think the next step is to recognize that we don't really have I1 and I2 anymore because there's no more choices. Every charge that's going to leave the battery only has one way to go. We could call that I total. So in reality, this circuit doesn't exist. This resistor is the combined effects of these two. And if we look at the 20 ohm resistor, I think we can really see what I2 is. The 20 ohm resistor gets both I1 and I2. The 20 ohm resistor gets I total. So I total is just I1 plus I2. Sometimes this is called the junction rule. And it's actually what we're after, because if we can find I total, we can start to get values of voltage and current, and we can use Ohm's law to solve. So I am fixing to be done with this circuit. I've just got one more combination to make. That is to recognize that these two are in series. So I have this very simple circuit. I'm just going to add those two together. This is going to be 42.22. And of course, it gets I2 going through. No, excuse me, IT. All right. So what have we accomplished with all that work? Our table's still mostly blank. Well, the battery gets the total current, and that's apparently something we can solve for now, because we have a total resistance of 42.22 ohms. And I can use Ohm's law to find IT. So V equals IR. I equals V over R. I is my total voltage of 48 divided by my total resistance of 42.22. So my total resistance is 48 divided by 42.22. 1.14 amps. And that's what the battery gets. It's also what the 20 ohm resistor gets. And now we're off and running. Now we can start filling out this table. So Ohm's law works with both the totals like we did down here. It also works with individual resistors. So I can find for the 20 ohm resistor, now that I have its current and its resistance, I can find its voltage. So its voltage is going to be 1.14 times 20. $22.8. So now we need to find something that's going to help us determine anything about these guys. We can't use Ohm's law because we don't have two things. But what we do know is that in a series circuit, the voltages all have to add up to a total. And if we look at this circuit right here, this is a series circuit. My battery, whatever voltage is in my 20, and whatever's left over for the parallel, they should, the 48 should cancel out these other two. So I'm going to do that. I'm going to say V total should equal V1 plus V2. This is sometimes called the loop rule. And I'm going to say 48 equals 22.8 plus V2. Well, minus the 22.8. And we get V2 is 25.2. I'm looking back over my shoulder because we just did this in HBark, so making sure I'm getting the same numbers. All right, so this parallel resistor gets the 25.2 volts. So what is that in the real circuit? It's the 40 ohm and it's the combination of the 15 and 35. So we don't know the voltage of either of these yet, but we do know the voltage of this 40 ohm. These two branches are in parallel, so they're each got a voltage of 25.2. So we got that going for us. Once again, do what you can with what you got. I can now find a current through the 40. So V equals IR. 25.2 is I times 40. So that tells me the current here is 0.63. So what is the 0.63? Well, it's the current through the 40, which is what I had labeled as I1. So I'm going to put it in red like I1 is. And my solution to what the current through the other two is, I2, is right down here. The junction rule tells me I total is I1 plus I2. Well, now we have I total and we have I1, so we should be able to find I2. Remember, the whole path splits into the red and the blue. So the total should be the sum of the two together. So the junction rule tells me 1.14 is 0.63 plus I2. And that tells me that I2 is 0.51. Notice it goes through both of them, so it gets both of them. So then the last step is just kind of cleanup. Just do V equals IR for these guys. And you'll get final answers for both. All right, that's what we got in class. So I'm not going to spend time showing you how to get the power. The power is really pretty much always the last step because we're just going to use the equation P equals IV. So you could multiply each of these together to find out how quickly each resistor uses energy. I hope you enjoy this. Students either love it or hate it typically. It's very much like your crossword puzzle. You got to have a bunch of tricks in mind, but they don't necessarily come in the same order. Just to summarize real quick, draw your currents, determine what possible pathways there are, use colors if you can. Simplify your circuit down to one resistor, get a total current, and then start solving anything you can. The things in your bag of tricks are Ohm's law, V equals IR, the junction rule, and the loop rule.